Today we're going to talk about, first we're going to talk about different types of compounds, molecular versus ionic, and then we're going to talk about formulas, different kinds of formulas, empiric formulas, molecular formulas, and then we'll finish up by talking about a brief conversation about concentrations. So in order to understand the different types of formulas, you have to, or not formulas, but compounds, you have to understand the different types of chemical bonds, because the different chemical bonding structures lead to the different types of compounds. So a chemical bond is an attractive force between atoms that is strong enough to enable a group to act as a single unit. And a chemical bond is essentially what occurs to form a compound as opposed to individual elements. It determines the physical state of the matter as well as the shapes and properties of the component units of the matter. So the types of chemical bonds are extremely important because depending on the type of chemical bond, you can have different types of matter and different properties. The molecular shapes are important in determining the types of intermolecular forces that are present. Notice the term intermolecular. What that means is that if you have a molecule from one compound and a molecule from another compound, or two molecules from the same compound, there are forces that interact in such a way as they would be attracted to each other. And these shapes help determine how those molecules interact. So the types of chemical bonds, the first are determined by the valence electrons that are available and how they interact. And remember, a valence electron is an electron in the outermost shell of the atom. The groups on the periodic table have the same number of valence electrons, and that causes them to have similar physical and chemical properties. So all of the atoms that are in group 1A, which is the column on the far left of the table, all have a single electron in its valence shell and all give up that electron in the process of bonding. On the other side, if you look at 7A, which is right next to the noble gases, which is the far right, the column next to that is 7A, also called the halogens. They have 7 electrons in their valence shell, and they want to just add one more to make an even 8. Elements react in such a way as to achieve 8 electrons in their outer shell, and this is called the rule of octet. This is only different for an element like hydrogen that only has 1 electron and then adds an electron in order to get 2 in its outer shell, or loses an electron in order to form none. And this rule of octet, or 8, in the outermost shell is done by either gaining, losing, or sharing electrons. So if you give up entirely an electron or 2 electrons, or if you take entirely 1 or 2 electrons, this forms what's called an ionic bond. An ionic bond occurs when electrons from one atom are totally given up to another atom, and in the end, both atoms have 8 electrons in their outermost shell. This results in one of the atoms becoming positively charged, the one that gives up the electron, and it's called the cation, and one atom gaining electrons, it's negatively charged, and it is called an anion. This occurs when there is a significant difference in electronegativity, and I'll explain that a little more in a future slide. Usually, this occurs when a metal atom reacts with a non-metal atom. That is, when something on the left side of the periodic table, such as sodium and potassium, react with something on the right side of the table, something like chlorine or bromine. And it forms a lattice structure like this. This is a molecular structure showing the ionic bonds between sodium and chlorine in the compound sodium chloride, which is table salt. The diagram on the left shows that the arrangement is such that it maximizes the charges that interact with each other, negative to positive. The smaller spheres in this diagram represent the sodium ions. The larger spheres represent the chlorine ions. The smaller spheres are purple and the larger spheres are green. And what you can see here is that it's regular geometry, like a box, also called a lattice structure. And what holds everything together is these negative and positive interactions. And these are bonded together such that one chlorine atom is surrounded by 6 sodium atoms, and one sodium ion is surrounded by 6 chlorine ions. In an ionic bond, an electron from a sodium is entirely given up to the chlorine so that it results in a sodium ion, which has, you'll notice, 8 electrons in its outermost shell now, conforming to the rule of octet. And there are now electrons in this outermost shell. And you notice this slightly bigger one represents the one that was exchanged with the ionic bond. And this occurs when you have a wide separation between the elements on the periodic table. So if you combine something from this side of the periodic table, which is a metal, and something on this side of the periodic table, which is a non-metal, these will form together such that they have an ionic bond. Now, if you look, example here, this is that C and O are close together. It does not form an ionic bond. And we'll talk about this a little bit more in the next few slides, but it forms what's called a covalent bond. This side is highly electronegative. This side is low electronegativity. And so, as I said in that one slide, the wide difference in electronegativity leads to a loss of an electron by one atom and a gain of the electron by the other atom. Ionic bonds frequently result in crystalline solids at room temperature that have very high melting points and very high boiling points. And what this tells you is that the attraction that's set up in the formation of an ionic bond is a very strong attraction. When these are liquid or when these are in the liquid form, they will conduct electricity because the ions or the electrons can move freely in the structure. However, when they're solid, they do not conduct electricity because the electrons are frozen in space. These tend to be soluble in water because water is a polar solvent. And what that means is that water has a positive and a negative end. And because it has a positive and a negative end, it interacts well with the positive and negative charges in the crystal and can break them apart. Water solutions, because the ions float freely in the water, will also conduct electricity because you have sodium ions floating around in the water and you have chlorine ions floating around the water. An electron comes in, it is grabbed by the sodium and transported through the water easily. Non-polar solvents, things like alcohol, oil, benzene, will not dissolve an ionic substance. And that's because the non-ionic aspect of the solvent cannot pierce or interact with the ionic character of the solid. Now, I mentioned in the periodic table slide that there was another bond called a covalent bond. A covalent bond occurs when two or more atoms share their electrons. So one atom doesn't give it up entirely and the other atom doesn't take it entirely, but there's a sharing that's agreed upon, and this is generally done in pairs. The sharing may be equal, resulting in a non-polar bond, and in most cases it's modestly unequal, meaning that one of the two atoms keeps the electrons longer and more stringently than the other. The more similar the electronegativity is, the less polar the subsequent bond is. And the more dissimilar the electronegativity is, then the more polar the bonding is. This usually occurs when two nonmetals combine. If you remember in the previous slide, I showed you carbon dioxide, which was carbon and oxygen are both nonmetals. So here's an example of two non-metal substances. Hydrogen is not a metal, even though it's on the left side. It's unique in the fact that being at the very top, it's a non-metal. And chlorine, which is on the non-metal side on the right. And basically there's a sharing between the hydrogen, electron on the hydrogen and electron in the chlorine. And what this shows is that because chlorine is larger and the electron spends more time with the chlorine, that this is a polar substance, with the positive pole being toward the hydrogen and the negative pole being toward the chlorine. So the distribution of electron density in this molecule is not even. There's more electrons around the chlorine nucleus than there are around the hydrogen nucleus, and this results in a positive pole on the left side and a negative pole on the right side. And this positive pole is designated by a lower script Greek delta plus and a lower script Greek delta minus for the negative. This helps to show you the general trend in electronegativity that occurs in the periodic table. And what you can see, first of all, if you look at columns, look at the column on the left, you see that electronegativity decreases as you go down the column from lithium down to cesium and francium. As you go across from left to right on any row, you'll see that the electronegativity increases, so that from potassium to bromine, you see that there's a significant change in electronegativity. The point here is if you combine two substances that are close in electronegativity, you tend to get a sharing. If you combine two substances that are far apart in electronegativity, you tend to get an ionic or non-sharing situation. So electronegativity differences result in the either ionic or polar nature of a bond. And what you can see, if you look particularly at the diagram that's in the upper left, is first of all you see electronegativity differeces, 0, intermediate, and large. The bond type that occurs is either pure covalent, meaning that it's nonpolar, polar covalent, meaning that sharing occurs but the sharing is not even, or ionic, meaning that there's a total transfer of electrons. And it gives you a very, on the right here, it gives you a little table that shows the sort of electronegativity differences that are associated with different gases, liquids, and solid. Or when you have a covalent bonding situation, the substance that results is generally a gas, liquid, or solid that has a low melting point. In the liquid state, it will not conduct, or gas state for that matter, it will not conduct electricity. It's insoluble in water, generally insoluble in water. Aqueous solutions of the substance, such as if you take table sugar, which is covalently bonded, you dissolve it in water, in the situations where water will dissolve it, they do not conduct electricity well. They are more soluble in nonpolar solvents such as alcohol or benzene than in polar solvents such as water. And then they can form more than one pair of bonds depending on the number of electrons, number of pairs of electrons that are transferred or shared. The last of the bonds that I want to mention is the metallic bond. And a metallic bond occurs between two metal atoms. And generally what happens is the two atoms come together and donate a pair, one or two electrons, to something called an electron C. And this is a form of sharing, but it's a much freer sharing in that it's not just between two atoms, but it's between all the atoms that are represented in the substance. It's metal to metal atoms, and it's atoms with similar electronegativity. However, they both have low electronegativity so that everybody's trying to give up electrons. And the properties come from the fact that the electrons are not localized. So let's take a look at what this looks like. First of all, these substances are very good conductors of electricity. They are very good conductors of heat. They are both malleable, which means they can be hammered into shapes, and ductile, which means they can be drawn into wires or strings. They are shiny and frequently highly reflective. And they have both high melting points and high boiling points, so that the attraction between the atoms is quite high. And this is what I'm talking about when I talk about the donation of electrons. You can see the electrons just freely travel throughout this sea, and the metal nuclei, or the metal atoms, are just sitting in this sea of electrons that float around. And because of that, electricity can pass through very easily. Heat can pass through very easily, and these things can slide on top of each other, so they're malleable and bendable. And here's just another example or representation of this electron cloud.